Let's try that there. That hopefully should work, I hope. All right, we're going to pick up where we left off in terms of chapter 17, I think is where we're at. As usual, if you do have questions, feel free to ask them down in the chat box and we'll get to your questions. And we're going to go through here, hopefully chapter 17, and then we'll get into 19 as well. All right, so I think where we left off last time was we were talking about sort of batteries at the end there. We finished up sort of really talking about galvanic cells and the calculations that involve those. Again, a reminder that you need to know galvanic cell, what makes it up, the different parts of a galvanic cell. Obviously, you need to do the calculations like we've been talking about, things like calculating E of the cell using the SRP values. Also need to be able to sort of, again, relate the E of the cell to thermodynamic type properties like delta G that we talked about. And obviously as well, equilibrium constant, its relationship to that. And obviously we also saw towards the end in terms of calculation part, the Nernst equation, which again, you could use sort of in non-standard conditions. So again, something's not perhaps 1 molar in terms of concentration. Something is not 1 atmosphere in terms of pressure. So again, that Nernst equation is sometimes used there in those type of conditions. So we also talked about batteries and different types of batteries. Again, a reminder that you're not going to be asked any type of like half reactions for any of those batteries specifically. Basically, you need to know sort of batteries, how they are similar and a little bit different to galvanic cells or a traditional galvanic cell. And, that's sort of the extent of what you need to know about batteries. So where we left off here is with corrosion. So let's talk a little bit about corrosion. Corrosion is sort of returning their metals to their natural state. About 1/5 of iron or steel production is made to replace rusted metals. And pretty much all metals that have an SRP value that is less positive than oxygen will be susceptible to going through corrosion. So really the basis of that is what we've been talking about with our galvanic cells. So if you remember when we look at sort of our SRP values, and in the lack of any sort of reaction information given to us, we can know that the more positive value should be our cathode, while the negative value, or the more negative value, I won't say that, I guess less positive, I guess is the better way to put that, less positive value would be our anode. So basically what it's saying here is all metals that have a SRP value that is less positive than oxygen will go through basically corrosion. And what that means is in a scenario where you put a metal and oxygen together, if oxygen is more positive, oxygen would be our cathode, the metal would be our anode. And what that essentially means is the metal is going to go through oxidation, which basically will be corrosion, and it will go through that sort of naturally and probably spontaneously as well. And again, that would lead to obviously corrosion happening and that metal perhaps degrading as well. Now, most metals, when we do go through corrosion, doesn't always necessarily mean it's a terrible thing. Actually, in certain cases, when a metal would go through corrosion or oxidation, if you will, it actually can protect the metal from future corrosion. An example would be aluminum. So what happens is as the aluminum sort of goes through that oxidation state, it forms this sort of protective skin, if you will. And that basically will protect the metal underneath from further corrosion. So, not all corrosion necessarily is a terrible thing. It can actually protect the metal from further corrosion. But the problem is in cases like, for example, iron, when iron goes through corrosion, what happens is it does make this layer, but the problem is the layer will fall off. And obviously, it kind of makes this rusty protective-ish layer, not really much of protection, but the problem is eventually it will fall off And when it does, it exposes new fresh metal to continue to go through that oxidation process. And obviously that will fall off. And until eventually, obviously, you don't have much metal left there. Now, sometimes oxidation will cause things that we commonly will see. So copper, for example, when it goes through oxidation, will make that nice sort of patina color. Silver or tarnish, that's silver sulfide. Now, gold with an SRP value of 1.5 volts is larger than oxygen. So gold, for example, will not go through corrosion because, again, when we hook up gold to oxygen, because gold is more positive, gold actually becomes our cathode and our oxygen becomes our anode. So oxidation actually occurs on the oxygen. Thus, the metal there, gold in this case, is okay. Now, in terms of sort of rust, basically there's a lot of non-uniform surfaces on iron, and these are great areas where oxidation could kind of occur. And it really kind of happens in a kind of a two-step process, but basically what you need for rust is you need iron, a little bit of moisture, and some oxygen, and that's pretty much all you need for this process to sort of kick off. So iron will go to iron 2 as the electrons kind of flow down, and then the iron 2 actually will get further sort of oxidized, if you will, to iron 3, and eventually make iron 3 oxide, which is what we commonly refer to as rust, as this picture shows here. You got these areas, these kind of pitty areas, where the iron 2 can then go to iron 3, a little bit of oxygen, and again some moisture there from the air as well. Sort of provides all you need for that formation of rust basically to occur. Again, the problem with rust is it kind of falls off, right? And again, exposes new metal underneath. And I'm assuming by the big money bag over here, costs a lot of money, right? Obviously, to replace these things as they get rusted out, and has to redo them. Now, there are some ways that you can prevent corrosion, for example. Here's just a few different ways we'll talk about. You could do some type of coating of the surface, which obviously would protect the metal underneath, hence things like Rust-Oleum paint, right? You paint it so it hopefully will prevent further rusting of the metal or whatever you may be painting. You could also do some type of galvanizing, for example, with zinc. So since zinc is a more active metal than iron, everything sort of happens at the zinc. So I guess what that means is if we kind of look at the SRP values, for example, here. In comparison, if we sort of coat something with zinc, for example, because zinc is actually more positive, I'm sorry, let's start again. In the comparison, iron here, between iron and zinc, iron is more positive. That means that iron in the case would end up being the cathode, while the zinc would end up being the anode. And thus, again, all the oxidation, everything will occur basically at the zinc. Again, here, protecting the iron from going through any substantial oxidation and sort of corrosion. So as it says there, zinc sort of acts as a sort of sacrificial coating. It allows all the sort of oxidation and bad stuff to happen to the zinc. And then obviously the iron, which is probably the main sort of structural component of whatever you have there, basically will be sort of protected as basically everything's happening to the zinc part of it. You could do some alloying of stuff, adding some chromium and nickel in there, for example, will change the standard reduction potential of something like stainless steel, for example, making it more like a noble metal. Again, noble metals like gold, as we just saw there, basically will not go through any type of oxidation or corrosion. And sometimes they'll use what is referred to as sort of cathodic protection. So, for example, if you take something like magnesium and sort of connect it to a wire to a sort of tank that's maybe buried under the ground or something like that, obviously that would be an environment where there's a lot of moisture, there's iron, right? And there's obviously some oxygen down there as well. So it by itself would probably go through a lot of corrosion if nothing was sort of done for that. But what we have when we sort of connect the magnesium, it's a better reducing agent. So remember that reducing agents, right, are the things that are getting oxidized. So they're the guys that are getting oxidized. So when we hook this magnesium up to this sort of iron tank, all of the oxidation again here will occur at the magnesium side, again leaving the iron that's sort of in that tank alone, if you will, and not going to basically corrode. Same idea, titanium and ships are used there to help prevent sort of oxidation caused by the salt water. And here's sort of a picture of that. Again here, by hooking this sort of magnesium to it, this is where all of our oxidation will occur. And again, leaving our sort of buried tank over there happy and perhaps not so corroded and stuff like that, which obviously if you're using that underground, like in this picture, is probably storing something and you wouldn't want that tank to fail. So stuff inside doesn't leak out, obviously, and stuff like that. So in terms of corrosion, you need to know what sort of corrosion is. You do need to know basically, you know, a couple of ways there to prevent corrosion. Any questions on that? Okay, so the last part of the chapter here, we're going to talk about electrolysis. And electrolysis is basically the process where we use some type of electrical energy to cause a non-spontaneous process to basically occur. So again, by providing sort of an electrical source or an outway electrical source, we could kind of make a non-spontaneous process sort of occur. So for example, sodium chloride here, what we know under normal conditions and normal sort of things, this sodium chloride normally will not break back into sodium metal and chlorine gas. And that's usually not a really spontaneous process. We don't really have, you know, salt sitting out that automatically becomes that, because that would not be so good. Doesn't even happen under sort of normalish conditions, right? When we heat it up, typically if you heat up salt, right, you don't get the chlorine gas or the sodium, which is good. Otherwise, those fries would probably not taste so good, I suppose. But we can do something like running a sort of a battery or electrical current through something like sodium chloride or even water, as we'll see in just a sec. And we can sort of get it to go through what is known as electrolysis. So in the case of something like sodium chloride, as we can see here, we could put in our sodium chloride, and by sort of running electrical current and all that good stuff, and maybe some other issues in terms of pressure and stuff like that, we can actually generate chlorine gas and sodium basically to come out. Again, that's not a normal sort of spontaneous process that will basically occur. But again, as you can also see here in a more simplified version, by running that electrical current, we're going to get on our anode side, our chloride going to lose those electrons and come this way, again, going from -1 to 0, going through oxidation, while the sodium will actually pick up those electrons, going from +1 to 0 over here, and basically get reduced. And again, we have our oxidation and reduction reaction that's happened here, kind of like a traditional sort of galvanic cell, but again, slightly different because we're kind of forcing the reverse reaction to happen, if you will, by providing that electrical current to do so. You could also do this with water. So here's an example of water. Very simply, you could actually do it. You take some water and like a 9-volt battery and some electrodes, and you actually can basically break apart water through electrolysis. Again, also a normally non-spontaneous process. Again, in normal conditions, when we play with liquid water, we typically don't get the hydrogen gas and oxygen gas back from it. Again, if you were boiling your water to make pasta or something like that, that's also a very good thing. Otherwise, you might not get to the pasta part. But again, if you simply sort of run an electrical current through it, you're basically causing, again, here in both of these cases, a chemical change to occur. So the chemical reaction is going to occur. Basically, a chemical change is going to occur. And we can see we will break apart our We will break apart our oxygen and our hydrogen. Again, oxygen in this case going from -2 to 0. So it is losing electrons and becoming more positive, while our hydrogen here is going from +1 to 0, and it is getting reduced on this side here. And we see the bubbles here in these two test tubes here. The bubbles are the oxygen gas and the hydrogen gas that's being generated. And in this particular case, in the void volume is where we would have the gas. We also sort of see something that we kind of know about water, perhaps. We do see we get perhaps twice as much hydrogen to oxygen. And again, if you think about the formula, right, you got twice the hydrogen for every 1 oxygen. So typically when you do sort of run through electrolysis, for example, water, you will typically see that you'll see that twice as much hydrogen being produced than oxygen gas. Now, when we do the electrolysis of water, and sometimes in questions when they're basically implying that you're doing the electrolysis of water, sometimes in questions they won't always sort of just straight out say they're doing the electrolysis of water, oddly, but they will, as you can see here, have something to do with an acid. So sometimes people will do this experiment. We've done this experiment before. And usually what you need to use is sort of an acidic water, if you will. So the acidic water, you know, kind of increases if you want to sort of think about it here, the H plus concentration there in the solution, and that increase in that H plus concentration again helps the reduction part sort of occurring, and again helps kind of pull those electrons from one side to the next. And usually if you see something about electrolysis cell was run with sulfuric acid, or usually sulfuric acid or some type of acid there. Usually what they're referring to is the electrolysis of water. And if you need the half reactions, again, these are usually the half reactions that you would use in that particular case. Now, if we run an electrolysis cell, for example, there is kind of several steps that you can do to calculate, for example, how much product you would make. You will typically kind of do these guys in a sort of normal order. In a lot of cases, they will give you the current for the particular cell. So they'll say, hey, this cell was run at 1.5 amps, which again is a current. And it was run for, 4 hours or something like that. How much sodium did you produce? And we can use some relationships that we kind of know here. A coulomb is equal to an amperage times a second, which means since they typically will give you the amperage, an amperage is a coulomb times second, which also means that typically in these problems, when they do give you the time, and again, a lot of times they'll give you like how many hours it ran for, maybe how many minutes, you usually need to do a conversion into seconds. And again, that's going to help you here. Because again, if you take the amperage, which is coulombs per second, and you times it by the seconds that you ran it for, that will give you basically the coulomb of charge that's basically associated with that particular electrolysis cell. Now, once you have the coulomb charge, what you could use is this guy here, which is basically Faraday's constant, right? And we can use Faraday's constant by dividing by that 96,500 number that we used previously. And that will cancel out the coulombs. And that will leave you moles of electrons. And it's really at this point, once you get to the moles of electrons, that you will deal with usually the two half reactions that you have. So like usual, you may have one half reaction, that's the oxidation half reaction. You may have a half reaction that is the reduction half reaction. And in both of those half reactions, you will have at some point the relationship, for example, between, say, a metal and electrons, right? So for example, if this was the half reaction, we could say there's 1 mole of electrons per 1 mole of the metal. So you're going to use that kind of moles of electron to moles of the metal or non-metal, if you're looking at the non-metal, for example. And you're going to use that relationship to basically go from moles of electrons, almost just like stoichiometry, if you will, to moles of what you're interested in. Again, I'll go metal or non-metal, probably in a lot of cases. Or it could be both metals, actually. So it could be 2 metals that you're dealing with as well. And basically that will give you the moles of the metal. And at that point, you technically will be like down to here in terms of this sort of path that we usually will follow. And at that point, you could do a variety of sort of ending calculations, if you will. If you're looking for grams, you would use the molar mass, right? You go grams per mole and get the grams of the metal you would produce. Now, if we were doing something like we just saw on the previous slide there, something with water, for example, where we produce oxygen gas and hydrogen gas, when we deal with gases, sometimes we're interested more in volumes. And that usually will involve us to use our good friend PV equals nRT, the ideal gas law, where we would solve for V, which would be nRT over P. The N would come from right here. So the N would obviously come from here. And then in the problem, they would obviously give you the temperature and pressure sort of information. And again, probably something like, hydrogen gas, oxygen gas, you could try to figure out, how much volume of each of those gas, how many liters of each of those gas you would produce. So these are sort of the pathway in these sort of electrolysis problems. You take the current times the time. Again, you want to make sure everybody's good in terms of units. So usually you just got to convert the time into seconds. That's going to give you your coulomb of energy. You're going to divide by Faraday's constant, which will give you moles of electrons. And then you want to go to the balance half reactions and figure out the moles of electrons to the moles of what you're interested in, be that a metal, could be a gas, could be a non-metal in that particular case. And then once you got that at the end, you'd have a variety of options. You can either figure out the grams using the molar mass. Again, if it's a gas, you can try to figure out the volume using something like the ideal gas law. Any questions on those problems? Obviously, this as well, sometimes these problems you work backwards. So you're like told how much you produce and you can just kind of work sort of these problems in a backwards sense. So why don't we look at one here and see what you got going here. So if we run a cell at 1.26 amps and it's passed through for at 7.44 hours, we want to know, you can write the half reactions and calculate the volume of a gas, each of the gases at STP. So I'll give you a second to do that, and what I'll do for you is also give you the reactions, which I think are on your notes. So those are the half reactions there, so I'll let you pick up with the problem. I'll write the information down for you here. So again, basically we are running this for at 1.26 amps for 7.44 hours. We're looking really for the liters of oxygen and hydrogen gas. So take a minute or two, get started on it, see how you're doing, and then we will talk about it. Okay, so let us take a look and see how we're doing. So we're basically trying to find, again here, the liters of both of those gases, hydrogen gas and oxygen gas. And like I mentioned before, if we could just go back for a second, I think. So if we look at this problem here and we read it, again, there's really no mention of water, for example. And again, the way you sort of know that is it just mentions something about sulfuric acid. So again, sometimes in problems, especially with the water electrolysis, they don't kind of straight out kind of tell you they're doing the electrolysis of water. But again, they typically will mention something to do with an acid like sulfuric acid or something like that. Or they may even say acidic water, for example, or something like that. So that's sort of how you know it. So, these problems sort of start very similar, a lot of them. We're going to take our amperage, which is the current that we're running it at. And remember that an amp is also a coulomb over a second. So that's a good little conversion there. As we talked about earlier, we need to cancel out the seconds. So when we look at our time, we're at 7.44 hours. So we do want to do that conversion. In an hour, there's like 3,600 seconds. And again, this is all just to make sure everything in terms of units really do cancel out. And looks like we'll end up with 26,784 seconds. So what we're going to do basically is times those two things. The seconds will cancel, and that's going to give us our coulomb of charge associated with this cell for that many hours. And it looks like we do end up with 33747.8 coulombs. This is where, again, we're going to use really that constant to convert from coulombs to moles of electrons. And that's our Faraday's constant, basically. Again, our coulombs will cancel each other out. So we're going to do a little 96.5. And we'll end up with something like 0.3497 moles of electrons. Any questions on the calculations up to this point? Now, really at this point is where you sort of decide what you're interested in. And in this particular problem, we're actually interested in both things here. So this is where we're going to use our half reactions. And again, you want them probably to be balanced half reactions to go from moles of electrons to moles of each of the substances we're interested in. So for example, if we look at our anode reaction here, in terms of oxygen gas, for every 1 mole of O2, you get 4 moles of electrons. So much like stoichiometry, for our moles of O2, we start with our electron moles. We're just going to use that half reaction again as a conversion factor. So 1 mole of O2 gets us 4 moles of electrons. Moles of electrons there are going to cancel. And if we take that and divide it by 4, we end up with 0.0874 moles of O2. We could also do the exact same calculation here for our hydrogen. So if we do our hydrogen, our moles of H2, again, going to the half reaction where the H2 is, if you look at it, there is a 4 here, which should get distributed in all the way across. And if you distribute that 4, what you end up with is 4 moles of electrons, gives you 2 moles of H2. And a 4-to-2 relationship is the same as a 2 moles of electrons for every 1 mole of H2. So really you could use either one there. Obviously, it'll give you the same mathematical answer. So again, starting with our moles of electrons, using our relationship that we got from the equation, and I'm going to use the 2-to-1 relationship. Again, you can use the 2-to-4 relationship if you like. Now it's going to give us our moles of hydrogen gas, which is going to be, looks like 0.175. And again here, now that we have the moles of each of those guys, if we wanted grams, for example, we could go to the periodic table and use the molar mass, and we can calculate, obviously, the grams of each of those guys. But in this case, we're actually looking for volume. So we are going to use the volume. A reminder that if you have STP, that is standard temperature and pressure. That means the temperature is 273 Kelvin and the pressure is 1 atmosphere. And that means that we can, if we want the volume of hydrogen, use the ideal gas law, PV equals nRT, and solve for V, which would be nRT over P. Putting in our moles of hydrogen, which is 0.175. R is our gas constant. Remember, when you use it for the ideal gas law, it is this number, not the 8.314 number. And our temperature being 273 Kelvin, all divided by 1 atmosphere, which is our pressure. And if we do that, we end up with something like 3.92 liters of hydrogen gas would be produced in this particular case. Now, that is the hydrogen gas. We could do the exact same calculation for the oxygen gas, but we also don't necessarily have to use the ideal gas law in this particular case. And that is because if you remember, perhaps, that at STP, 1 mole of a gas is 22.414 liters. So you actually could use that if you like instead for both of them. So you could take the volume of oxygen gas, in this case would be the moles of oxygen. Again, using that conversion, which can only be used at STP conditions. And you will end up with 1.96 liters of O2. Again, you could put it into the ideal gas law just like we did above. The only difference is obviously you would use the moles of the O2 in that particular case. Any question on that calculation? We also see what we talked about before. If you compare the amount of hydrogen gas that was generated in the cell to the amount of oxygen gas, it is a 2-to-1 relationship. Yeah, we got twice as much hydrogen produced than we do oxygen in this case. Any questions on any of that calculation where we got any numbers or anything like that? Okay, so why don't we try one more here before we wrap this chapter. All right. So why don't we, we want to know how much calcium will be produced in this electrolysis cell if we run molten calcium chloride through a current of 0.452 amps for 1.5 hours. Here's the half reactions. So again, why don't you take a few minutes here and see what you come up with. Here we are looking for the grams of calcium, and calcium is 4008 on the periodic table, which you might need. All right, take a couple minutes, then we'll talk about it and see how everybody did. Okay, I just want to make sure you can hear me. Yes, just make sure. Yeah. Okay, I think that's better now. I think, hopefully. All right. So we have our amperage here that we do want to convert to coulombs per second. And again, we're going to have to convert our hours into seconds as well. So everything matches up here. So again, we'll just do our 3,600 seconds. And that will get us, by multiplying perhaps, that'd be good. There we go, 5,400 seconds. So same sort of beginning part here. We're going to take this, we're going to multiply it by 5,400 seconds. That is going to get rid of our seconds and leave us with 2440.8 coulombs. Again, here we're going to use basically Faraday's constant and divide by the 96.5. And that's going to convert us into moles of electrons, which gets us 0.0253 moles of electron. In this particular case, we are just interested in the calcium, so we just need to focus really on this half reaction here, and we can see from it that for every 1 mole of solid calcium there, we get 2 moles of electrons. So that's going to allow us to go from moles of electrons that we just calculated to moles of calcium. Again, very much just like stoichiometry, if you will. So we're going to divide that by 2, 0.0126. And in this particular case, we're looking for the grams. So we are going to use the molar mass from the periodic table here. And that will convert us into grams, which looks like, we'll call it 0.51 grams, 0.51 grams of calcium would be produced in this particular cell if we let it run for 1.5 hours. Any questions on that calculation there? Now, in this particular case, we weren't maybe asked about the chlorine, but we might have been asked about something like the volume of chlorine, maybe even the grams of chlorine. So if we were interested in chlorine, again, we could have picked it up from here, used the mole to mole relationship between chlorine and electrons, which is 2 moles of electrons per mole of chlorine. And that would get us to the moles of chlorine, which again, in that particular case, you could either use the molar mass of chlorine to figure out grams, or if they gave you some information about pressure, temperature, or something like that, you could have figured out the volume of chlorine gas you would produce as well. Any questions on electrolysis problems? Again, sort of a variation on this problem would be, for example, they said something like, hey, you produce 0.5 grams of calcium in this cell that ran for 1.5 hours. What was the amperage? Or, they may say you produce 0.51 grams of calcium at an amperage of 0.452. How long did you let the cell run for? So sort of the variation of this electrolysis problems would be sort of really just sort of working backwards. So again, that's sort of a slight variation on these type of problems. Any questions on electrolysis or how to do the calculations? Okay, so that should, I believe, wrap that chapter. So that is good. So what we're going to do is go off to the next chapter, which is chapter 19. So just give me a sec here to get to it. that should work. All right. Okay, so in this chapter here, chapter 19, as it says there, we're going to talk a little bit about transition metals, just some reminders on transition metals. Then we're really going to get into sort of complex ions and coordination compounds. We're going to talk about what those are. We're also going to talk about, how to name them and all those fun stuff. So the first part here is hopefully a lot of it should hopefully be some review, I hope, in terms of transition metals. So obviously transition metals are located on the periodic table between groups 2 and 3. And one sort of trend that we sort of see, just in general, is something that's known as effective nuclear charge. So perhaps you're familiar with effective nuclear charge, but essentially what effective nuclear charge is the charge that an electron feels as a result of what is sometimes referred to as screening or shielding. So for example, if you got a positive nucleus and you got some electrons in that first energy level, and you got some electrons in the second energy level, for example, and let's just say this is a positive 3 charge in terms of the protons. When we look at these electrons, which are closer to the nucleus, they feel pretty much that full positive 3 charge, right? But when we look at the electron that's beyond those guys, a little further away from the nucleus, because he has those other electrons kind of in his way, he doesn't feel perhaps that full brunt of that positive 3 charge. And what he maybe feels is more like a positive 1 charge. And that means he's going to be held less tightly than these electrons that are closer to the nucleus. And that's essentially what Z effective is. That's the effective nuclear charge. So basically, if you take the protons there and you subtract it from the electrons that are shielding them, you get that effective nuclear charge. For example, in this one, which by the way is lithium, that third electron, for example, in lithium is the valence electrons, right? And that's why valence electrons are removed easily. They're involved in bonding. They're furthest away from the nucleus. And because of this sort of shielding that occurs, they don't really feel the full brunt of that positive charge. And as you know, in terms of positive and negative charge, it increases in terms of strength as those numbers get larger. So as the positive and negative values get larger, so there's that strength of it. And what we see here is as we go kind of left to right on the periodic table, the Z effective gets larger, which means that even though those outer electrons are further away from the nucleus, they are being held tighter. And that's what we know as we go left to right on the periodic table. On the right-hand side towards the upper, those are our nonmetals. Those are guys that typically hang on to their electrons. They don't lose electrons. And guys to the left and down on the periodic table, they are bigger, they're further away, and those outer electrons are not being held as tightly because of this idea of effective nuclear charge. It's kind of like when you're in the movie theaters and somebody comes and sits down in front of you. You got your nice seat in front of the screen. Everything looks perfect. Guy comes in, sits down with a big cowboy hat in front of you, blocks most of the screen, and you essentially can't see as much of the screen as you were when nobody was there. So they're essentially shielding you. So as we can see here in general, as you go to the right, Z effective will increase. And as you go to the left and down, it decreases. And again, it has a lot of relationship in terms of size. Just in general, everybody is closer to each other over here, and thus going to hold those electrons a lot tighter. So here are our transition metals, again, between group 2 and group 3 on the periodic table. These are the guys that essentially will have a variety of charges associated with them, except for perhaps 3 of them that are there. And again, a reminder that everybody has a variety of charges except for zinc, which is +2, cadmium is +2, and silver typically will make a +1 charge. So everybody else, for the most part in that transition metal region, will have a variety of charges. And that's why when we do name them, right, we do use those Roman numerals to indicate the charge that we find on those transition metals. Here's another shot just in case. You also may know that these guys are sometimes referred to as inner transition metals because technically speaking, they should go right about there and right about there in terms of periodic table and their location. So when we look at transition metals, they show very great similarities within a given period on the periodic table. And also within, obviously, a vertical group, they share very similar sort of properties when we look at them. When they do form ionic compounds, they typically, as we've talked about, have more than one oxidation state, which again is why we use those Roman numerals when we name them. And cations are often found in what we refer to as complex ions, which we'll talk more about at the end of this chapter or towards the middle of this chapter. And complex ions are essentially a metal that's positively charged, and attached to them are what are known as a bunch of ligands. And ligands, if you remember, we touched upon it, are what are known as Lewis bases. And Lewis bases are things that are electron pair donators, right? So they donate a pair of electrons. While a Lewis acid is something that's electron deficient and it's able to accept a pair of electrons. And here's an example of a complex ion, which we will learn to name in this chapter as well. And it'll take up the whole screen, but we'll learn to name it anyways. But basically, you have your positive cobalt here, and the NH3 here are the ligands that are attached to it. The overall thing has a +3 charge. Again, NH3 is neutral, and it basically, that +3 comes from the cobalt that's in the middle there. Now, most compounds are colored because of the presence of the transition metal, and really also depending on sort of the ligand that's attached, you may see some different sort of properties. Many compounds are paramagnetic. Paramagnetic means you have a lot of unpaired electrons, right? Or at least one unpaired electron. Diamagnetic means that they are paired up, all the electrons, right? Going in opposite directions in terms of their spin. When we do electron configuration, again, what happens is when we do get to our transition metals, that is basically our D block, right? Our S block is over here in group 1 and 2, 3, 4, 5, 6, 7, and 8. As I run out of periodic table, we'll fix that. That's our P block, right? In terms of electron configuration, the 2 rows there on the bottom are our F block. So when we look at transition metals in terms of electron configuration, they start at the 3D, right? Because that's the first energy level that we actually do see d electrons occur. And if we follow perhaps that little zigzag thing that maybe you learned, hopefully, in your chemistry career, it looks something like this. Right, and kind of zigzag to write the electron configuration. And what we typically see is here we go from 3p to 4s and then back to 3d. So again, those d orbitals get the electrons after the 4s orbitals in that particular case. And while we're here talking about electron configuration, s orbitals, right, holds a maximum of 2 electrons, right? P orbital to fill up all 3 of them, that is 6. D orbital to fill up all 5, that's 10 electrons. And F, if you fill up all 7 of the F orbitals, you can max out at 14 electrons, right? Now, there is some exceptions to the normal sort of electron configuration that we commonly see and experimentally. Yeah, paramagnetic, to answer your question, paramagnetic means when you do your electron configuration, for example, If you remember, you've done like an orbital diagram, for example, we'll just say, hey, this is 1s, 2s, say 2p, right? Orbital diagrams typically boxes or lines with arrows, right? Yeah, they go in something like this. So paramagnetic basically means, for example, you have a lot of unpaired electrons, essentially. So those guys on the right, these are unpaired. These guys are what are referred to as paired, right? And that is because of their spin, right? When it goes up, the spin quantum number is plus a half, right? When it goes down, the spin quantum number is minus a half. And so if you sort of end up with something like that, where you have some unpaired electrons, that is sometimes referred to as being paramagnetic. These electrons have spin as their own sort of electrical field and stuff like that that's affected. If everybody's sort of paired up, if you will, that's what's sometimes referred to as diamagnetic. Basically, all the spins sort of cancel each other out. All the positive halves and negative halves basically cancel each other out. And it does have some effects on some of the properties of elements and so forth, depending on whether or not they're paired off or not. Now, when we do look at electron configuration, there's a couple of exceptions to normal electron configuration. And two very common ones that most people sort of look at is chromium and copper. And chromium, copper, they actually have one less electron in the s orbital, one more electron in the d orbital. And that happens because, as you may also know, when the electrons get filled, the 4s is lower in energy than the 3d. So the electrons go into the 4s first, then they start filling up, the 3d. But these guys are very, very close in energy. So it's not that hard for an electron to sort of be elevated up to the d orbitals. And then it's just been found experimentally that chromium and copper are more stable in that sense. So their configurations, instead of ending at 4s2, 3d4, or 4s2, 3d9 for copper, they actually have those extra electrons up in the d orbitals. You may also know, perhaps, as we'll talk about as well in just a second, but once you do start actually filling the d orbitals with electrons, there's actually a switch in terms of energy. And what ends up happening is the 4s electrons actually become higher in energy than your 3d. And this is why perhaps sometimes if you're learning electron configuration or you searched around maybe on the internet or whatever, you'll sometimes see people write electron configuration in what people sometimes call it's all in the correct order, or everything goes together like 3s2, 3p6, 3d4, 4s2. All these guys sort of go in order. And it is correct in the sense of electron configuration in terms of energy. But in this class, previous classes, and probably most classes that you take, you typically don't write the electron configuration like that in terms of energy. You write it what is sometimes referred to as the filling order, how the electrons actually go in to the atom, which is this order here, which is why we end up usually will be putting our electron configuration very badly written there. Let's try it again. 1s2, 2s2, 2p6, 3s2, 3p6. That's why we typically will write it like this, and you usually should, where the S's come before the D's. Again, here, that's the filling order and usually how you write electron configuration. But sometimes you will see people write it based on energy rather than filling order. But usually filling order is the way that most people will write it. By the way, if you go sort of underneath copper and chromium on the periodic table, there's a lot more exceptions to the normal electron configuration. So things like silver and those type of guys. So if you kind of find where chromium and copper is on that periodic table, drop below them, you will also see a lot of exceptions to the normal electron configuration. Again, you'll even find some that have 0 electrons in the s orbitals. They've all been sort of promoted upwards to the d. So most people in most classes that you take in terms of chemistry will focus kind of just on that first row and the copper and the chromium. But again, there is a lot of sort of exceptions that do occur, and they all kind of occur a lot of times underneath those guys on the periodic table. When they do form ions, so as I just sort of alluded to, what happens is once we start putting those electrons into those d orbitals, and again, although they do go into the s first, we do see that switch in energy that does occur. And that's really important for when these guys start to lose electrons. So, for example, when these guys start to lose electrons, what's going to happen is they will lose their s electrons first. So they'll lose those s electrons first. And if they need more electrons at that point, then they'll go into the d orbitals. So transition metals are a little bit different than sort of our representative elements, which are found on the outside. You can, in the transition metals, typically always lose those s's first and then dip into the d's. And that's different than sort of representative elements where, typically speaking, you lose those last electrons in the electron configuration that you write. But here is different. So if we look at Ti, here's the electron configuration. This again is noble gas configuration. And again, even though this is the correct order, what happens is these guys sort of switch in terms of energy. So when it goes to a +3 charge, it basically has lost 3 electrons. So the first 2 electrons is going to lose, is going to come out of the 4s. And then that third electron will come out of the d, and that is going to leave us the correct configuration here for Ti with the +3 charge of argon 3d1. So again, transition metals all the way through there will essentially lose the s or electrons first and then go into the d if necessary. So why don't you write the correct electron configuration for nickel with a +4 charge? And while you're at it, why don't you write it for iron with a +3 charge? Iron's atomic number, in case you're not sure, is 26. And nickel is 28 in terms of its atomic number. So why don't you take a second and write the electron configuration for each of those with those charges. Okay, so let us take a look. We'll start with the nickel. So if we do nickel with no charge, that is 28, which means 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Now, nickel with a +4 charge means that it has lost 4 electrons. So again, here we're going to take out 2 electrons here, and the first ones are going to come out of the S. And that means we still need to lose 2 more electrons here as well. So we will end up with 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 as this configuration. Now, if we look at iron, which is 26, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Iron again here with a +3 charge. Again, first ones out are our S's. We then need to also take out 1 more electron there, and that would leave us 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 in that case. Any questions on that? So hopefully that should be something that's reviewish to you. Yeah, it's perfectly fine if you want to use that. Just for practice, it's been a while, so I write it all out there. But yeah, you could use the argon and continue on with the but in the case of nickel, it would then be argon. We got there 3d6, and it'll be argon 3d5 for the iron with the +3. Other questions on that? Our electron configuration involving our transition metals. Okay. All right, so let's just finish sort of talking about transition metals here and some trends. And again, here for these trends that we're going to sort of talk about, um, you just need to know the general trends. You don't necessarily need to know any specifics in terms of numbers or anything like that. And again, some of this stuff I would hope would probably be some review type stuff for you for some of the stuff that perhaps you hopefully covered there in 50. First sort of trend, if we look at the first row transition metals, if we look at our oxidation states or numbers, we do see a variety of oxidation states as you go across that first row. So this is our first row on the periodic table. There are transition metals, where 3D is basically. Number 21, right? If you look on the periodic table, this is guy 21 right there. And we do see a lot of oxidation states really kind of maxing out there in that first row there at Mn as you solve, and maybe as you're starting to work through that redox experiment, you can see from that table as well, Mn can have a lot of different oxidation states, anywhere from +2 to +7 in terms of its oxidation state are numbers. The most common ones here are in red. So as you can see, though, in general, as you go across the transition metals, most commonly in terms of oxidation states, +2s, +3s are very common. But you do see sort of a common sort of rise as you go to the center there of common oxidation states heading from +3 to +7. And then it sort of comes back down on the other side. Another trend that we commonly do see for transition metals just in general is ionization energy. So a reminder, ionization energy is the energy that's required to remove an electron in the gas phase. As you may know as well, or maybe you don't know, but ionization energy, electrons do come off one at a time. So for example, magnesium, the first thing that would happen is magnesium would drop an electron. And there would be an ionization energy for that. It's sometimes referred to as the first ionization energy. And then what will happen is this magnesium will then drop off its second electron. And there's actually an ionization energy for that second electron to come off, which is known as the second ionization energy. And in general, when we talk about ionization energy, it does increase as we go from the first electron to the second electron to the third electron. And if you think about just looking at magnesium, for example, magnesium started with no charge, but once you pop off that electron, a couple of things are happening. You now have magnesium that has a positive charge. So greater nucleus charge, going to bring everybody in as well, right? So cations are smaller in size than their neutral counterparts because they lost electrons. So everything contracts, which means our second electron is now finding itself closer to the nucleus and also closer to a sort of larger positive charge than was there, just a second ago in a sense, because it's nearer it. And it's going to be held a lot tighter. So we typically see that if you look on this chart, as you go from the first ionization energy to the second, you see a very big increase for each of these elements. And as you can see as well, as you drop to the third ionization energy, to the fourth ionization energy, you continue to see that trend continue again. As it continues to lose electrons, everything gets smaller, electrons get closer to the nucleus, held a lot tighter, takes more energy to do that. You also see something, for example, like sodium will do the same deal. It will lose an electron, have the first ionization energy. Then that next guy would technically lose an electron. And that would be its second ionization energy, right? And when we look at the difference here, though, as we go from here to here, we are now like a 10 times the difference in terms of energy. That's an incredible amount of difference. And that typically does not happen under normal conditions, right? When we think about sodium, it is typically only a +1 charge, because as soon as sodium loses that first electron, we are now into what are referred to, right, as core electrons. And if you remember perhaps from bonding, there's valence electrons, right, which is outermost electrons, the ones involved in bonding. And then those core electrons, which are closest to the nucleus. So typically we can't remove those core electrons very easily. It takes a tremendous amount of energy to try to do that. And under normal conditions, these things don't happen. So that's why, for example, if you look at magnesium, you go from 735 for the first electron, it almost doubles to 1445 for the second. But then when you go from like the second to the third, it's almost now 7 times the amount of energy to do that, and about 10 times the amount of energy to remove that first electron. And again, once you get to that third electron for magnesium, you're now into the core electrons. And again, typically doesn't happen. So what we commonly see in terms of trend is as you go from left to right on the periodic table, again, ionization energy increases. And as you go down, the ionization energy decreases. And that makes sense as you go up and right on the periodic table. Those are our nonmetals, which typically will gain electrons. They typically don't lose electrons. And so it takes a tremendous amount of energy to try to remove electrons. And that's the general trend that we see here. This should be going left to right on the periodic table. And when we go that way, we do see an increase in the ionization energy as you go left to right on the periodic table. Here's just a bunch of trends, which obviously you should memorize everything. I'm just kidding. Don't send me the emails. You don't have to memorize any of these numbers, obviously. But what we see in general with this is electron configuration. Again, we're increasing electron configuration. There's our couple of exceptions we talked about earlier. In terms of atomic radius, also something you should be familiar with, right? As you go to the right and up on the periodic table, everybody gets smaller. These are our first, second, and third ionization energy. Again, gets larger as you go down, and also larger as you go across. Larger as you go down in the sense of first, second, and third ionization energy. So again, more energy to remove those electrons. Second electron, third electron, and so forth. And also, again, increasing in ionization energy as you go left to right on the periodic table. Here's our common oxidation states as we talked about. Again, +3, +2, very common. We do see a general decrease in melting point and sort of a general increase in density as you go across. Again, you have more protons and those type of stuff as you go to the right, which gives it more mass and sort of a a volume also increases as you go to the right. Here's just some graphs of these ionization energy. The blue dots are the third ionization energy. The red ones are the first. And what we see is, again, the difference between first and third ionization energy. The first ionization energy is the energy to remove the first electron. The third ionization energy is the energy to remove the third electron. So as we just talked about, significantly higher in terms of ionization energy as you start removing the first to the second to the third electron in a sort of element. And here's all three of them together, first, second, and third, in case you missed the second one here. Why not? We'll include them here. So here's our second. Again, you can see our second is higher than our first, while it is lower than our third. And again, our general trend as you go left to right on the periodic table of increasing in terms of ionization energy. Now, electron affinity is another sort of trend that you probably should be familiar with as well. When we think about sort of ionization energy, that's the energy required to remove an electron. And when you remove an electron, you basically become a cation, right? Positively charged. So a lot of times we look at ionization energy as sort of a measure, if you will, of the ability to form a cation. While electron affinity is different, by the way, than electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. But electron affinity is actually the energy change that occurs when an atom gains an electron. So when an atom gains an electron, it will become negatively charged, and that's an anion. So usually electron affinity is sort of a measure of the energy change that occurs when something becomes an anion. And what we typically see is, for the most part on the periodic table, electron affinity increases as you go to the right and decreases as you go down. And this is group 7, and it's not perfect electron affinity. As you can see, it increases and then kind of slightly goes back down. But the general trend is it's increasing as you go up and to the right on the periodic table. Again, not perfect in this particular case. And here's another table of that. This is a table of relative reducing abilities of those first row. And what we see is the reducing ability increases here as we go to the left. Reducing ability, right, means that these things will get oxidized, right? As you go that way. You may also look at these things and go, wait a sec, isn't the most positive guy going to be our cathode and get reduced? And you would be right, but these are not SRP values, right? These are sometimes what is referred to as standard oxidation values, basically. These are oxidation half reactions, right? And these oxidation half reaction electrons are on the product side. And what we see here is actually the more positive one here in terms of oxidation is the one that's going to get oxidized. So if you turn these all into reduction SRP values, you would reverse all these reactions and the signs would change. So the top guy would be negative all the way down, and the bottom guy would become a positive, which means in terms of what we know for SRP, this guy would most likely be reduced down here and be a better oxidizing agent, right? As you go that way. So just to remind you, if you happen to look at this a little bit later on or something, or look in your notes, these again are not really SRP values like we were talking about in those tables in the last chapter. These are actually all written as oxidation reactions. So it's the opposite effect here. The more negative here, in this case, would actually be the cathode or the one being reduced, while the more positive in this case would be the one being oxidized. So in terms of radius as well, it gets smaller as you go left to right on the periodic table. As we can see here, in case you're not sure what those guys look like on that table here. That's what each of those elements look like in the first row transition metals. and these are oxidation states and some of the colors that you typically see. And I'll just roll through that because, you know, we don't really have to worry too much about these guys here. Any questions up to there? Okay, so we're going to stop here for lecture with chapter 19. And I think what I'm going to do is for today, since I think in terms of lab and everything, we're kind of on schedule in terms of what you need to know and stuff like that. I'm going to lecture on the sort of the rest of this here, some of the naming parts and stuff like that for lab, just to kind of keep us on pace as we're getting, you know, to the end. Actually, I think we only got a few more weeks to go, perhaps. So I just want to make sure that we are able to cover all this stuff. So we'll take a break and then we'll continue lecturing in lab, and I think that will probably be it, you know, in terms of what we're going to do today. You should still have out there, obviously, I think the titration experiment. You should also have the redox experiment, which is out. And I think in lab, we'll talk a little bit about the next one that I'll post either today or so, which will be the electrochemistry, which again, at this point, I think you should be able to do with no problem, and that'll keep everything going. So in terms of scheduling, I believe next Thursday is the next exam, which covers through this chapter. So again, I think I do want to lecture here today in lab, again, just to keep us on pace so we can make sure we cover everything we need to, and we don't have to move too much stuff around. So that's coming up. And then a reminder as well, your presentations should be coming up as well. I almost want to say probably a couple of weeks from today. Yeah, it's going to be June, and I think that's when they're scheduled. So hopefully you're working on that as well. So the plan will be we'll lecture on this stuff, hopefully make a pretty good dent into the naming and all that kind of stuff and what's left of this chapter. And then we'll kind of cut out lab early, and that'll give you time to go work on everything that you need to kind of get accomplished. And again, a reminder, don't forget about that final project, which is coming up. So hopefully you're working on that as well. So obviously you have a lot to work on and keep you busy, but we will devote a little bit here of the beginning part of lab to kind of finishing this chapter so we can kind of stay on pace. Any questions on any of that stuff that's happening? Okay, so we'll take a little break here and we'll start about 11:40 for lab. And again, we're just going to continue lecturing on this, and I think that'll be it. Any questions on anything? Okay, I'll see everybody in about 20 minutes or so. And again, make sure you go back through the lab link.